Hey guys, this is the visual video to go along with chapter 6, which talks about the interactions that take place in the tube. So this is actually how x-rays are created. All right, now I don't want you to pay attention to this right now. I was just trying to save paper, so I'm going to start up here. So they tell us that 99% of what takes place in the actual tube is heat. Remember, that's 99% of a ridiculously large number. All right, so when we're talking about that 99%, you're talking about millions of billions of electrons that have the potential to bombard that target. So what happens, you've got the focusing cup over here made of nickel, you've got the filament that's thorium and tungsten, and then you've got your electron cloud or your space charge right here. So when these electrons have kinetic energy and they bombard that target, they tell us that some of the electrons don't interact. They just simply pass by. And this is where I use that example. I said to you, if there's a group of guys or a group of girls and the opposite sex walks by, no interaction, just comes close, gets this electron excited, raises it to a higher energy state, and then it passes by. But it has to get rid of that excess energy by giving off heat in the form of infrared radiation. So when these electrons bombard, some will actually interact, some will pass by. So this is actually called an excitation, because what happens is that excitation, that electron, the filament electron, or the incident electron, or the projectile electron passes by, raises this outer shell electron to a higher energy state. It has to get rid of that excess energy, and it does so in the form of infrared radiation or heat. And this is what happens the bulk of the time. Okay, so that's our first and most prominent interaction. Then we will go to characteristic interaction. Okay, and the characteristic interaction also takes place. And what happens is you've got, again, your focusing cup over here, your filament, your electron cloud, or your space charge. And they're getting ready to bombard this target. So this is tungsten with 74 protons, 110 neutrons. And then you've got K, L, M, N, O, and P shell. And I didn't draw them all out, but K shell has 2 electrons, L has 8, M has 18, N has 32, O has 12, and P has 2 electrons. And then the binding energies are in green. You've got 69.5, and that is keV. When we look at that, it's 69.5 keV, kilo electron volts, 12, 3, 0.6, 0.08, and 0.02. Okay, now those come into play because characteristic is an ionizing interaction, all right, meaning it's going to knock out an electron. So let's say that one of these filament or projectile or incident electrons is going to come in, all right, because we're only going to talk about one at this time. Even though millions of billions bombard the target, all of this is happening simultaneously, okay? So what's going to happen is, let's say this electron makes it through, because remember, you're talking about this, right? This atom and these shell levels are constantly in motion, and all of those electrons are all over the place. So whatever this hits, it's not nice and flat and drawn out like this. It's more in constant motion like this, which means that when that electron comes in, whatever it interacts with is what's going to happen. So let's say this electron makes it all the way in, and it removes this K shell electron. Okay, this is where it's headed. And this, in order for that to take place, remember we said that the kinetic energy has to be greater than or equal to the binding energy. So let's just say we're set on the control panel at 70 kVp. Okay, so we're set at 70. This electron comes in, it's equal to or greater than 69.5. So it's actually going to knock this electron out. And when it does that, okay, this becomes an ejected electron. So that ejected electron is just knocked out of its orbit. So what does it do? It basically leaves a void right here, correct? That would have a hole. And that atom then becomes ionized because there's loss of an electron. It also becomes unstable. So what will the atom do to try and regain stability? Ideally, it's going to fill that void with whatever electron is closest to that void. So let's just say, let me just use this. Let's just say that this one fills it. So this one jumps up, fills that void. When it does, it releases a photon of energy. Then what? You get a void here, correct? So one of these, let's just say one of these fills that void. Every time it releases a photon of energy. Leaves a void, next one fills it, releases a photon of energy. Void, one to fill, photon of energy. Notice my photons are getting longer wavelength, less frequency. Void, fills it, really long wavelength flow. So what do you end up with? You end up with a void in the outermost shell, okay? So at the end, we call this the characteristic cascade, correct? So every time an electron jumps a shell level, and they can only go forward, they cannot go backwards, every time that happens, it releases a photon of energy. At the end of that cascade, though, you have an empty shell, a missing electron. Can we leave it like that? Absolutely not. What has to happen is that has to get filled. Well, how does it get filled? Because nothing can go backwards. This is where the ejected electrons come in, because once that gets knocked out, it's likely to fill a void in another atom, because at the end of the exposure, everything has to go back to stability, meaning all of these atoms on the target, all the tungsten atoms have to go back to stability. They need 74 electrons again in order for it to be stable. So one of these ejected electrons is probably the one that's going to fill that void. Hopefully that makes sense. Now, I also told you in lecture that it's not likely that each successive shell fills, but just for the ease of the drawing, we'll do it like that. I also said in the lecture, you can calculate the energy of that photon that we created, correct? How do we do that? It's the difference in binding energy from the shell level that got ejected from the shell level that replaced it. So in this case, we ended up with 69.5 got ejected, and what replaced it? 12. So we subtract 12 from that. Okay, so we end up with 5 minus 0 is 5, 7, a 57.5 kVp photon. What happened in the next? We just kept doing it, right? So then L shell gets knocked out for this one. L got knocked out, and M replaced it, which is 3. So it's 12 minus 3. What do we end up with? A 9 kVp photon. And we can keep going. So then this one got knocked out, which was 3 minus 0.6, which leaves me a 2.4 kVp photon. Next one, we end up with a 0.6 minus 0.08. So we end up with a 0.52 kVp. Hopefully you're getting the idea of what's happening. So really long wavelength. This is way more penetrating photon than these are out here. And then the last one, P, ends up being a 0.08 minus a 0.02. You end up with a 0.06 kVp photon. Okay, Now, if we were set at 70 kVp, this one is likely to be useful to us, correct? Because if we're at 70 and all these, the beam is polyenergetic, this one will likely use. This one and the rest of them, not likely to be used. Why? Because only the K shell emission is useful. Does it mean you'll only ever get 57.5? No. What happens is if K shell gets knocked out, any shell level can replace it. So let's say K got knocked out, K got ejected. All right, so let's just call it 70 because we'll just round it off. So if that one got knocked out, and let's say P replaced it, because that would yield us the most energy, right? So it's 70 minus 0.02. What would that give me? That would give me a 69.98 kVp photon. Now that is useful. That is useful. If K gets knocked out and any other shell level replaces it, minimally you're at 57.5 to 69.98 is the range of energy. And that's why K shell is the only one that's useful. What about when these other ones get knocked out and we get these really low numbers? That's where filtration comes in, right? So when you are radiating a patient, you want the most penetrating photons to go through the patient. In theory, you want it to go through. You don't want it to stay in them. You don't want to add dose to them. So these all end up being filtered out in the tube, in the housing, in the collimator. But ideally, we filter them out because if they made it out of the tube, all this would do is add skin dose to your patient. These are not going to help create your image at all. This definitely. Something like this, yes. And if K was replaced with any other shell level, like this was K out and replaced by L. If K got knocked out and was replaced by M, you would still end up with a 66.5 kVp photon. That's useful. If 69.5 minus 0.6, minus 0.08, minus 0.02, anything then any shell level can replace K, and we're going to end up with something useful. Why do I say it's an ionizing interaction? Because there's a removal of an electron, all right? Hopefully that makes sense to you guys. Sorry to walk in front of you like that. I'm just gonna move this over here because I feel like you can't really see me, and I'm just trying to, it's not about me. I feel like the camera actually fell, so let me go back up with that. All right, hopefully you can see that. So just to reiterate, if K shell gets knocked out, any other shell level that replaces that is going to be useful. It's going to make it as a photon in the primary beam. If any other shell level, will the other shell levels get knocked out? Absolutely. Because remember, millions of billions of electrons bombarding this target, all interacting at the same time within milliseconds. So these are going to get knocked out. But the photons that are produced, not useful to us in the beam. So when they're produced, they ideally get filtered out in the filtration that's built in to the tube, the housing, or the collimator. So that's why we keep saying in diagnostic radiology, only K shell emission is useful. So if that gets knocked out, any other shell level that replaces it is going to be beneficial to us. These ejected electrons are likely to fill the void that's left at the end of the characteristic cascade. So this process of all the electrons filling the void is called a characteristic cascade, and at the end of the cascade, always the outermost shell is left with a void. In this case, we would say P shell. If we had a different target element, it might not be a P shell, it might actually be a different shell level because the element would change. What's our next interaction? Brems. Okay. Our Brems interaction. Brems is non-ionizing. All right, so no shell level is going to get knocked out for this, But what will happen is there's a degree of attraction between the negative electron and then what charge does the nucleus have? Positive, right? Because there's the protons that are in there. So it's a degree of attraction between the negative electrons and the positive nucleus, but it's not ionizing. So for this, let's just say that our control panel is set at 100 kVp. All right, so what happens? This, let's just go with this first electron, comes in, and this negative electron is attracted to this. Let's just say it makes it all the way as close as it possibly can to the nucleus. And in order to do that, remember I talked about the concert? In order to get there, it has to give off every single bit of its energy in order to be there. So what happens, I'm just showing you the direction, when it's attracted that way, all of that energy is given off in the form of a photon. So it entered with 100, it gave up everything. So if it gave up all of it, what you would end up with is 100 kVp photon. Because all the energy was given up in order for it to get that close. All right, let's look at the purple one. So these make a little bit more sense. Still set at 100, but now this one's going to come in and it's going to come close to the nucleus, kind of wrap around and then exit. Okay, so it starts off coming in with 100, but let's just say it left with 40 keV of energy. So what did it do? In the meantime, it had to get rid of energy by passing that close. So if it started with 100 and it left with 40, this must be a 60 kVp photon. Why? Because mathematically that plays out. And with Bremsstrahlung, I ended up telling you guys that with Brems, it's the difference, hang on, let me fix this for you. It's the difference in binding energy between it's the difference in kinetic energy between the entering and exiting energy of the electron. Okay, so it's the difference between the entering and exiting kinetic energy of that electron. So if it went in with 100, it gave it all up, then it ends up being 100 kVp photon. If it went in with 100 and it left with 40, then it would have yielded a 60 kVp photon. And let's just say that this one, entering with 100, right, so it's going to come in, it gets kind of close, and it takes off. So it goes in with 100, let's just say it left with 70 keV. What would it have given off? A 30 kVp photon. Okay, so there's no ionization in this interaction. It doesn't knock anything out. It's simply a degree of attraction between the negative electron and the positive nucleus. So the more time and the closer it spends to the nucleus, more energy is given off. Right? You can also look at the angle. This one is a tighter angle than this one. So how do you calculate it? The difference between the entering and exiting kinetic energy. So on the green one, oh, this silly camera keeps falling. I'm so sorry. Bear with me. Okay, so on this green one, okay, let's just say we're saying that we went in with 100 and we had 0. So 100 minus 0 gives you 100 kVp photon. That's how we got the green one. The purple one, it entered with 100 and it left with 40. So it left us with a 60 kVp photon. And then the red one went in with 100. Sorry about that. Left with a 70. 70. So what did that yield? That yields a 30 kVp photon. So you get all kinds of energies with Bremsstrahlung. We said you can get from 0 all the way up to your maximum set kVp. How do you get the maximum? By it coming as close as it possibly can and giving up all of its energy. But you can get everything in between. That's how we end up with a polyenergetic beam, right? Meaning multiple energies. Polyenergetic, multiple energies. All right, and that is Bremsstrahlung. Now, the only other thing I want to point out, if this red one left with 70 keV, it could, in theory, go knock out a K shell of another atom and cause a characteristic interaction. Can that happen? Absolutely. So whatever energy it leaves with, it can go. It basically is going to keep going until the exposure ends. And remember, millions of billions of interactions all taking place simultaneously, and until the exposure ends or they run out of energy, like this electron no longer exists. These electrons still exist, so they can still go cause more and more interactions. This could cause heat. It could knock out LMNO or P and cause an interaction. This could knock out K shell and cause a characteristic interaction. So it keeps going. Okay? That is Bremsstrahlung. All right. Now let's look at filtration, because we said that with characteristic, right? With characteristic, we truly want to absorb or filter out these low energy photons. How do we do that? Filtration. Okay? So this is the housing, the tube, and the collimator. So we have what's called inherent filtration, and these are things found in the tube and the housing. So what kind of things do we find in the tube? We've got the glass, the borosilicate glass is in the tube. You've got the dielectric oil in the housing. You've got the different metals in the housing, right? All of those have the potential to absorb those low energy photons. So you've got the borosilicate glass, some of the metals in here could absorb them. The housing itself is made up of different metals. The oil can absorb it. So anything that's found within the tube or the housing is inherent filtration, built into it. Added filtration is what's found beyond the tube and housing. Anything beyond the tube and housing is added. Our biggest source is the collimator. What kind of things do we have in the collimator? We have lead shutters, which is number 82. We have silver on the back of the mirror, which is 47. There's a light bulb in there. There's some different metals in there. There's lead in the shutters. Tin on the back of silver on the back of the mirror. Different things that are in the collimator that also can absorb that low energy radiation. Okay, so all of this has the potential to stop that low energy radiation that would never make it out to do anything with our image. It would only add dose to the patient. Okay, and then there's also things that they talk about, compensating filters that you can add to the bottom of the collimator. All right, usually it'll have little tracks like this, kind of like on a stove, how you put the racks in, and then you slide the filter into that. So they gave an example of a wedge filter. What a wedge filter would do is allow more radiation to pass through the thin part, less will pass through the thick part, because the wedge is typically made of aluminum, and aluminum is number 13. Okay, so you put the thin portion of the wedge over the thick portion of the patient, and the thick portion of the wedge over the thin portion of the patient. So this will make you laugh, but if we had a foot, typically you would put the toes, 1, 2, 3, 4, 5. You would put the toes under because those are the thinnest, under the thickest part, and then you would put the ankle portion under the thinnest part so that you get more even penetration, more even exposure on your image. There's an example. This is called a double wedge or a trough filter. Literally, it's 2 wedges put together. Sometimes they use a double wedge when they're trying to image the thoracic spine, the T-spine, and then this would be over each lung. So sometimes that'll absorb some of the radiation so the lungs don't look so black, so that you can actually see the T-spine. And they also mention in the book a boomerang filter. All right, if you take the inherent filtration plus the added filtration, that will give you your total filtration. And remember, we said in there that total filtration on a general purpose tube, if you are operating above 70 kVp for the most part, then you need 2.5 millimeters of what they call aluminum equivalency. And that is set by the federal government. More specifically, it's set by the EPA, the Environmental Protection Agency, because they're responsible for guarding the public against unnecessary radiation exposure. So most of the tubes we work on have 2.5 millimeters of aluminum equivalency filtration. What does that mean? Aluminum equivalency. It means not everything that we mentioned, right? The oil, the glass, the lead, the silver, that's not aluminum, but it has the same absorption characteristics as if you had a piece of aluminum that was 2.5 millimeters thick. All of these things can absorb that low energy radiation, just like if you had a 2.5 millimeter piece of aluminum slid in there, it would do the same thing as far as the absorption. So it's 2.5 millimeters of aluminum equivalency, set by the federal government, specifically the Environmental Protection Agency. So from here down, this is our example of filtration, where you find it, what kind of things make it up. Anything that can stop a low energy photon from exiting the tube is going to be a good thing. Okay? Heat, 99% of the time, this is what happens. Just goes by, gets it excited. It gives off infrared radiation in the form of heat. Bremsstrahlung, non-ionizing, simply a degree of attraction between the negative electrons and the positive nucleus, and you calculate the photon energy by the difference between the entering and exiting kinetic energy. The entering energy is typically whatever your control panel is set at. The exiting is whatever it left the atom with. The result would have to be that number as a photon. That's what makes our beam polyenergetic, because BREMS can produce from 0 to your set kVp, and realistically only gives us our 70 kVp photons, our 69 kVp photons, because only K shell getting ejected is useful. Everything else is going to be filtered out, not this one. All of these get filtered out by that filtration that we just looked at, right? And that kind of takes us to the end of the visual video for chapter 6. Okay, so again, everything that ends up coming out in here in the primary beam is made up of K-shell characteristic interactions along with all of our Bremsstrahlung interactions. And remember, this happens the bulk of the time. They usually tell you if you're set at 100 kVp, 85% of the interactions are going to be BREMS, 15% will be characteristic. All right, that should do it. If you guys have any questions, be sure to get a hold of me, and I will hope that I can clear up any confusion. Thank you so much.